Okay, guys, today we're going to talk about all the different ways you can find delta H. But before we get into all the different ways you can find it, I wanted to start by reviewing a little bit about what H is. What is H? We see that a lot in this chapter. It means something. What does it mean? Enthalpy. Enthalpy means what, guys? Enthalpy means what? Heat energy, okay? And we learned that in chemical reactions, heat can either be released or absorbed. That heat energy can either be released or absorbed. So that's what this slide is about. Remember that enthalpy is the heat energy released or absorbed in a chemical reaction. So whenever you see H, you should think heat energy. It's enthalpy. So we like to talk about it in chemistry in terms of delta H. What does delta mean, guys? Yeah, delta means change. Okay, but how would you calculate change? How would you calculate it? You take the final minus initial. Please write that in your notes. I know it's not in there, but let's make sure we know what delta means. It means change, and we calculate it by taking the final value minus the initial value. So when we talk about delta H, it's really the heat energy that is either being absorbed or released in a chemical reaction. So it's equal to Q. And last lesson we learned what Q was. What does Q mean? Q means heat energy. So don't they mean the same thing, guys? They do. Delta H equals Q. Well, if delta means final minus initial, when we look at a chemical reaction, we're going to take the enthalpy of the products because that's the final, right? So if I have this reaction, A goes to B, which one's the product? Well, it's B. That's the final. That's what it is finally. So we take the enthalpy of the product, subtract the enthalpy of the reactants. It's the same thing as saying final minus initial. So delta H is equal to the enthalpy of the products minus the enthalpy of the reactants. Well, there's two types of chemical reactions. We've reviewed this a lot. Exothermic reactions, delta H is what? Delta H is negative. Because if you look at this exothermic energy diagram right here, delta H falls. So if you take the final minus the initial, you're going to have a negative number. So delta H is negative for exothermic reactions. Guys, can you just destroy this much heat energy? Where did it go? Yeah, it left in the form of what? Heat. Okay, so it makes the surroundings hot. Okay, let's contrast that to endothermic one more time. In endothermic reactions, delta H is positive. So here's an endothermic reaction diagram, energy diagram down here. If you look at where we start and where we end up, delta H is what? Well, it's positive. Can you just create heat energy? Where did it come from? It came in the form of what? In the form of heat. So the surroundings become colder in an endothermic reaction. Okay, we've talked about that quite a bit. Let's move on to something new today. We're going to talk about all the different ways to find delta H. So we've defined it on an energy diagram. This difference from where you start to where you end up is delta H. But there's a lot of ways you can calculate delta H. There's actually 5 of them, and we're going to go through all 5 in this chapter. Number 1, I think you're supposed to list them in your notes. Number 1 is stoichiometry. We've talked a lot about stoichiometry, so it should just be a review, but that's the one we're going to talk about in this video, in this lesson. Okay, stoichiometry. But there's calorimetry. Number 3 is Hess's law. We'll spend some time learning Hess's law in a couple of days. Number 4 is there's tables for delta H, and this little subscript F means formation. The delta H of formation. There's tables we can look this information up on because they've already been calculated in a lab. And finally, we can calculate delta H by looking at bond energies. So bond energies. Because bonds are being broken and then reformed, we can look at the bond energies to determine delta H, and we'll do that in the very last part of this chapter. Okay, so there's the 5 ways: stoichiometry, calorimetry, Hess's law, tables, and bond energies. We're going to talk about the first one today, which is stoichiometry. So let's talk about stoichiometry first, okay? Practice problem number 9. It's in your guided notes. Please be following along and write down everything that I write down. I've got a couple of extra ones after this that I would like you to do on a piece of scratch paper, but this one should be in your notes. Okay? So finding delta H by stoichiometry, it's pretty easy. It's just a review. I'm not going to spend that much time on it. So let's go through this one problem. Okay? It says when 1 mole of methane, guys, methane is the main component of natural gas. So we burn a lot of methane. Mostly in your furnaces at your home, but there's other ways we use methane as well. But when you burn 1 mole of methane at constant pressure, 890 kilojoules of energy is released as heat. Calculate delta H for a process in which 5.8 grams of methane is burned at constant pressure. So when you have these stoichiometry problems, it will tell you what 1 mole releases. So 1 mole of methane releases 890 kilojoules of energy. That's what we're going to use as our conversion factor later on in the problem. But you always start with the amount that they give you. 5.8 grams of methane. Okay, let's start with that. 5.8 grams of CH4. Put it over 1. Okay. We need to convert this grams into moles. So how do we do that? You guys remember how to do that? If grams of CH4 is on top, what's got to go on bottom? Grams of CH4. And we want to go to moles, so 1 mole of methane goes on top. How many grams of CH4 are in 1 mole of CH4? I guess what I'm asking, what's the molar mass of CH4? Yeah, you look at the periodic table, carbon is equal to 12 grams. Hydrogen is equal to 1 gram. Well, we've got 12 from the carbon plus 4 more from the hydrogen. That's 16 grams in 1 mole. Okay? So what we did there is now our grams of CH4 cancels out, and we just converted to moles of CH4. So all we did right there was convert to moles. Now what I'm going to do is use this as a conversion factor. 1 mole of methane releases 890 kilojoules of heat. So let's make a new conversion factor and find out how much heat it released. Okay, if moles of CH4 is on top, what's got to go on the bottom? Moles of CH4. Well, our conversion factor that we're getting from the information here says that 1 mole of CH4, so I'm going to put 1 here, releases 890 kilojoules of heat. So I'm going to put 890 kilojoules on top. But I need to put, it's releasing it, so is it going to be positive or negative? Negative. Yeah, our Q or the sign here, it's got to be negative because it's releasing that heat. So that conversion factor that we made, this one right here, in 1 mole of methane, 890 kilojoules of heat is released. Okay, you've got to be able to put that at the very end. And now if we look, our moles of CH4 cancel out, and we can cross multiply that and figure out how many kilojoules of heat will be released. So let's put that in our calculator. We got 5.8 times 1 times negative 890. So on the top I get negative 5,162. And on the bottom, what's 1 times 16 times 1? Well, it's 16. So let's divide those two numbers now. And I'm getting a negative 322.6 what? 0.63 kilojoules, yeah. So I'm going to put a kilojoules on the end. So that's how much heat would be released if you just burned 5.8 grams of methane. Okay. So did we have a complete mole of methane here? Did we start with 1 mole? How much was 1 mole? 16. So we didn't have a full mole, did we? So we're not going to burn, or it's not going to release 890 kilojoules. How come it's less than that? Because we didn't really burn 1 mole, so it's going to be less than that. And so negative 322.6 is less than 890. And that's why, because we didn't have a mole of it. We burned less than a mole. Now, what if I ask you this? What if we burned more than a mole? What if I started with more than 1 mole of methane? Yeah, it's going to be more than the 890. And so that's what our next problem will ask us. That's it for the guided notes, but I would like to go through a couple more problems with this, just to kind of help you get a hang of this. Okay, we did get the answer right. Negative 322.6 kilojoules of heat was released. Let's try this one. If you're watching the video, please try it on a piece of scratch paper. See if you can get this one right. So I'm going to give you guys some time. I want you guys to try this one on your own, okay? I did change it a little bit. Instead of, what was it, how many grams last time? I've got 250 grams this time. See if you can get this problem right. So if you're watching the video, hit pause, work the whole problem, get an answer, and then once you have an answer, hit play and see if you got it right. Okay, so let's see how you did with this problem. Again, it says we have 1 mole of methane. It's burned at constant pressure. It releases 890 kilojoules of energy. It wants us to calculate delta H for a process in which now 250 grams of methane is burned. So we're going to start there with 250 grams of CH4 and put it over 1. Now I need to switch this grams to moles. So let's make a conversion factor to do that. If grams of CH4 is on top, we know that it's got to go on bottom to cancel out. We're trying to go to moles, so I'm going to put 1 mole of CH4 on the bottom. And it's the same molecule as the last problem. What's the molar mass of CH4, guys? 16. Yeah, we got 12 from carbon plus the 4 from the hydrogens here. That's 16. Okay. And so now my grams of methane cancel out, and I've converted to moles. Now, I'm going to make one more conversion factor from the information they gave me in the problem. It said 1 mole of methane releases 890 kilojoules of heat. Well, if moles of methane's on top, we know that it's got to go on bottom. And that's what it's saying. 1 mole of methane releases, so I'm going to put a negative, 890 kilojoules of heat. So we have to kind of make this last conversion factor on our own from the information in the problem. Now my moles of methane cancel out and I'm left with kilojoules. That's my unit, which is what we wanted. That's what delta H is measured in, joules or kilojoules. So now we just got to cross multiply and see what we get. But before we do that, do we have more than 1 mole, guys? Yeah, 1 mole is only 16 grams. So what's your hypothesis? Is the amount of heat going to be greater or less than 890? It should be greater than. So let's see what happens. So we've got 250 times 1 times negative 890. Okay, I get that on top, and we got 1 times 16 times 1 on the bottom, so that's 16. So let's just divide that by 16. And I get this, so a negative 13,906 kilojoules. 0.25 kilojoules, but I'm just going to leave that off. So that's my answer. So delta H for this reaction is equal to a negative 13,906 kilojoules. What does that mean? Is it endothermic or exothermic, guys? It's exothermic. That's releasing that much heat energy. If you drew an energy diagram, let's going to start up here and it's going to come all the way down here. It releases, so this is my delta H right here. In this example, it's negative. It's exothermic. So my products, my CH4, had more energy than the products. My reactant CH4 had more energy than the products. So it's exothermic. So again, it's just one way to find delta H. It's by using stoichiometry. I've got one more problem I'd like you to try. Okay, and so yeah, we did get the problem right there. I've got one extra practice problem here I'd like you to try. So again, it's not in your guided notes. Please just solve it on a piece of scratch paper if you're watching the video. Try it first, okay? Try and get an answer, and then, so hit pause right now, get an answer, and then hit play and see if you got it right. Okay, let's see how you did. Let's read it. It says 1 mole of octane. Octane is the main component of gasoline, which has a chemical formula of C8H18, is burned at constant pressure. 5,460 kilojoules of energy is released in the form of heat. Calculate delta H. So we want to find out what delta H is for a process in which 2,804 grams of, this should say octane, sorry. Octane is burned at constant pressure. Guys, why did I choose 2,804 grams? Well, that's because that's the amount in 1 gallon. That's the mass of 1 gallon. So we're going to figure out how much heat is released when you burn 1 gallon of gasoline. Okay. Okay, so let's start this. What do I start, guys? What do I write down first?
2,804.
Yeah, let's write down the mass of that octane, which was 2,804 grams. And that's C8H18. Do you guys know why it's called octane? Because how many carbons does it have? 8. Okay, and that's for oct. And you put it over 1. Now we need to switch this to moles. So let's make a conversion factor and switch it over to moles. If grams of octane's on top, we know that it's got to come down here. And we want to switch to moles. So I'm going to put 1 mole of octane on the bottom. Now we just have to figure out what the molar mass of octane is. Okay, we've got carbon, so that's 12, but we've got 8 of them. So I'm going to take 12 times 8, and then add 18 from the hydrogens. Did you guys get 114? 114 grams of octane in 1 mole of octane. So what we did there, my grams cancel out. We've converted it to moles. Now we're going to use this conversion factor that it gave us in the problem. It said that when we burn 1 mole of octane, it releases 5,460 kilojoules of energy. Well, moles of octane's on top. We know that it's got to be down here. Okay. Again, when it says 1 mole, I'm going to put 1 mole here. Releases, so it's a negative 5,460 kilojoules of heat. Okay. And now my moles of octane cancel out. And we can cross multiply across the top and bottom and get our answers. So 2,804 times a negative 5,460. Yeah, I get minus. Okay, that goes on top. And we're going to divide that by what's on the bottom. So 1 times 114 times 1 is 114. So let's divide that number by 114. Did you guys get this? So delta H in this case would equal, what is that? A negative 134,297, if we round it to the nearest whole number, kilojoules. Did you guys get that? Okay, good job. Okay, so what does that mean? Is it endothermic or exothermic when you burn octane? It's exothermic. So, how do we know that it's exothermic? I mean, you've done this, you've drove a car. What happens when you're driving a car to your engine? It gets hot. It gets hot because this octane, when it's burnt, is releasing energy. It's exothermic, so the engine gets hot. what do you have to do in order to keep your engine at a safe temperature? You have to use coolant. So your radiator, you got to put antifreeze in there, and it cools the engine so it doesn't get too hot and ruin it, right? And so there's an example of an exothermic reaction. But guys, just another way to find delta H. Okay, we're finding delta H through stoichiometry. Can we do that? It's pretty easy. Pretty easy. Okay. Well, that's just one of the ways. In the next videos, we'll learn how to find it in using calorimetry, which is a different method. But anyway, hopefully this helped.